Hello and welcome to another episode of All Things IDA. This is again continuation of the previous two videos about Appcall, but this time we're going to be talking about Appcall and IDAPython and how we can use the same concepts we learned in IDC in IDAPython. In IDC, what we did to call a function is just make sure that we have the function in the database and it has a proper prototype, and then we can call it. In Python, we cannot just simply say underscore printf and say hello world, or let's say %s hello world, and expect it to work, because this is just not a valid Python method. The reason it works in IDC is because of the tight integration between the IDC interpreter and the kernel, IDA kernel. For Python, we have introduced a wrapper object to have this nice transparent way to interface with the API. So with this, we have to go through the Appcall global object. Here, IDAPI.appcall. This is the one we're looking for. In reality, as you notice, I prefer to use IDAPI for everything, but it is really coming from the debugger. So IDA_IDD. So Appcall is a singleton. You can think of it. Okay, so as long as we can prefix whatever we want to appcall with the appcall object, then we should be able to call it naturally. So for example, printf, what we did here, this is not gonna work unless we say appcall dot, and now we should see the side effect here, hello world, it got executed. So that's the only difference to begin with. Now, if you remember, we used to do look by name to resolve something and call it, and maybe then say apply type to permanently put a prototype. Or we were using dbg_appcall, passing the location, prototype, and then the arguments. So we have a better syntax for Python that lets us basically nicely initialize APIs once and for all and call them. So what we're gonna do here, we're gonna call load library again. So that's how we can initialize load library nicely once in IDAPython and use it in the script later on. So for example here, load library. Then what we do is we say it's going to be an appcall dot proto, that's the syntax. And we say what is the location we want to call. So we're creating an appcall prototype, so to say. And so our destination is going to be, we can pass a string that will be resolved to a name or an actual numeric address. So here we're gonna let IDA resolve that name, saving us time from calling get name EA, look by name, etc. And now we have to also pass the prototype. And that's it. So we gave the two important factors, the location and the prototype. So here let's say it's a H module, load lib, doesn't matter what's the name, and then the actual argument. And now I have a callable app call that has all the stuff it needs to do the app call. So now I have load lib. It's an object, but of instance callable. We don't need to care about those details. I'm just showing it to you. So here we say load lib. Now we treat it as a callable object, say user32.dll. And we got the same effects. And this is basically user32 being loaded, just like that. So we got like that proto, and it will work nicely. Similarly, if we are as well gonna be calling, let's say, record creation and so on, this will be a bit more understandable for you, a bit more than the generic object in IDC. So let me show you. So here we have two ways to actually call methods that requires structures. So if you remember, for example, print records requires a user record. We can call it through appcall and pass it a dictionary that has the attributes that we care to pass. So since user record takes an ID and a name, we can actually just create a dictionary with the attributes with the proper types, of course. So if ID was a number, we just put a number, and if name is a string, we just put a string. And then the second method, if I want to construct another object to pass to a function that we're app calling, it takes a structure. I can then also use the appcall.object constructor and pass the attributes in the constructor. So this is record 2. It has ID equal to, name equal this. Now, of course, if I put something that is not really part of the user record, it will be ignored. So if I say here, for example, last name equal ABC, it's meaningless. So that will stay in the Python object, but when IDA tries to make the app call, it will not be serialized into a native representation. So that will be ignored. These are relevant. So like this, I constructed two structures and I'm passing to the app call like that. Print record already has a prototype. I didn't need to actually do a typed object or a proto instantiation as I did earlier. So like this, it's fine. So we can run it. And here I got the two outputs, ID1 and ID2 coming from here. So that's a very intuitive way to construct objects and pass them to functions that requires them. Now, let me show you, for example, a bit more of a comprehensive example. The concepts are explained already from the previous two videos, and here we're just showing you the Python equivalent. So let's take a look at how we can have something more interesting. So here in this demo, I want to use a bunch of kernel 32 functionality. So as the first step in your scripts, usually you should have an initialization part. And like this, I'm initializing all the app calls that I need. I know they don't have a prototype because I just started the debug session. These addresses are from debug segments. They never have default prototype. So I'm prototyping what I need. And like this, I'm creating app callable objects. So here, get current directory really maps to kernel 32 get current directory. This is the prototype. Get Windows directory, set current directory, find first, find next as well, and find close. Now, this simple script, all it does is enumerates executables in the Windows directory and does some logic looking for a file. So first thing is we're gonna illustrate how we can call get current directory. So get current directory takes the buffer, output buffer len, and the actual output buffer. So how can we express that? How can we, in Python, in preparation to do an app call, create a buffer that we can pass to an actual API. So here we can use appcall dot. So A is an alias I did for simplicity. So A dot means appcall. So since I'm gonna be passing an output buffer, I have to use this special syntax. So appcall dot by ref, and please create a 260 bytes buffer initialized with 0. And then now I can call get current directory. I'm passing less than I want, so it doesn't matter. And say, okay, get current directory, and this is an actual buffer, and that's how we initialized it. You should be able to call it. And then the second thing, same story for get Windows directory as well. I created now in a different way. Instead of creating by ref bytes buffer like that, I'm also using another helper method called buffer. And this is like used normally for string buffers. It's just a helper function where we just have to pass the size, and internally it will create a by ref buffer initialized with 0. So really this appcall.buffer is really based on the by ref, but just a utility method. So same story, get Windows directory. But when we get the buffer, the nice thing about it, that it has dot size, and that's really convenient. So we created like a buffer object that appcall knows how to consume, and it has the size attribute. So here the difference is we are hard coding because we created like that one. I could have said len, for example, if len supports whatever that returns. And then once I get the Windows directory, I'm taking the len and not taking the rest of the buffer, just making sure I stop at the actual return, the buffer, just at the 0 termination. Then I'm changing the current directory to Windows directory. Then that's how we do a find first. Same story, appcall.empty object. So dot object in this case. Find first, start.exe, populate fd for me. Since we gave it an empty object, when it returns, it will have proper fields based on the fd type, which we defined here win32 find data a. So let's go to the structures window and insert the win32 find data a. So that's basically the buffer that we created appcall.obj, but since it's going to be an output argument, IDA knows how big the object should be. It passes an initialized object. The API goes, uses that memory with the proper size, fills in everything. When the appcall finishes, IDA goes to that memory location and retrieves the bytes, populates your object correctly so you can consume it. So the object in reality, after we do the app call, will have all those attributes. And if they were nested stuff with pointers, IDA will deserialize back to an object for you If they are linked, you will have .next, 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 etc. Now this is the thing. Once we get the fd.filename, which is gonna be just a buffer, we need some convenience methods to get that buffer as something we can consume in Python. So we ask another helper method, appcall.cstring, we give it a buffer, and behind the scenes, it takes that buffer and stops at the null terminator and gives us a Python string. So like this, if we ever created a buffer, at the return of the buffer, we can do either get the value as a raw buffer, as an array, or we can have a convenience, just give it to me as a C string. It will just enumerate and give you a string out of that buffer. And here we're looking for regedit. So as long as we can't find regedit.exe, keep an enumerating and then find close and restore the current directory. And we're gonna re-verify we're back to the original working directory, and if so, we're good to go. So let's run this script. It's gonna go to Windows directory, enumerate executables, stop enumerating as soon as it finds an executable containing regedit. And this is all happening in the context of the debugging. So if I was doing remote debugging, effectively you are doing like a remote control kind of thing. I could create a process remotely and so on. So here I'm enumerating either locally or remotely, as we said. So be careful using Appcall. If you're gonna use a debug server, maybe run your debug server with a password, for example. Now, let me talk about some possibilities, what we can do with this kind of stuff. There are so many things you can do with Appcall. For example, fuzzing, DLL injection, remote memory allocation, changing memory protections, and so many other things, really. I hope by now you can internalize the utility of Appcall. Going forward, there are more topics we can talk about Appcalls, so let's continue in the next video. Thank you, and see you next time.